Your firm has been hired to design a system that allows airplane pilots to make instrument landings in rain or fog. You've decided to place 2 radio transmitters 50 meters apart on either side of the runway. These 2 transmitters will broadcast the same frequency but out of phase with each other. This will cause a nodal line to extend straight off the end of the runway. As long as the airplane's receiver is silent, the pilot knows she's directly in line with the runway. If she drifts to one side or the other, the radio will pick up a signal and sound a warning beep. To have sufficient accuracy, the first intensity maxima needs to be 60 meters on either side of the nodal line, at a distance of 3 kilometers. What frequency should you specify for the transmitters? So first off, let's draw a diagram and see what this looks like. So here we have our 2 radio transmitters. So here's one, and then up here is the second one. They are a distance of 50 meters apart from each other. And I've shown the runway here in the middle. So this nodal line, again, is going to extend off the runway, a very large distance off the runway. So this is our nodal line. So this is where there would be perfect destructive interference. And then these little guys right here, these lines are antinodal lines. So this would be where the first maxima would occur. You can see as you get further away, they will extend out from that initial nodal line in the center. Now again, our transmitters are out of phase, so that means our inherent phase difference here is pi. And we're going to be checking a point P that I've marked here, that is 60 meters away from the nodal line and 3,000 meters away from the transmitters. Now in order to go through and figure out this problem, at point P there's going to be constructive interference. So that's what we're going to start with. So at that point, our 2 speakers will be in phase. Their phase difference will end up being 0 or a multiple of pi. But since it's the first maxima, we know that they're going to be a phase difference of 2 pi. So we are going to need to look at this first distance, R1, which will be 3,000 meters in the x direction. And if you notice, the distance from the runway to this first speaker is going to be 25 meters. The distance from the nodal line here, the same one we were measuring at this point, is 60 meters. So for the vertical distance, vertical as in on our plot here, vertical, is going to be 60 meters minus the 25 meters here. So 3,000 going across and then 60 minus 25. In order to calculate the distance R2, again we'll have 3,000 going across in the horizontal direction, but this time we'll have 60 meters this way plus the additional 25 it takes to get down to the second transmitter down at the bottom. So again, let's go ahead and take a look at the mathematics going on. So our phase difference is going to be the normal 2 pi, because we're talking about that first maxima point. Our horizontal distance was the 3,000 meters. Our vertical distance for R1 was, again, 60 meters minus the 25 meters. Distance formula. And we find that that distance is 3,000 0.204 meters. That second distance has the same 3,000 meter horizontal distance. And that vertical distance now is going to be 60 meters plus 25 meters. Distance formula, and we find that this distance is going to be 3,001.204 meters. So the path length difference between these two, R2 minus R1, will end up giving us 1 meter. So, plugging this into our phase difference equation, we know that since we're talking about the first maxima, that it needs to be in phase, so that's 2 pi. This is going to be that's going to be equal to 2 pi times our path length difference plus the inherent phase difference of pi, since our loudspeakers are inherently out of phase. Now we can subtract 1 pi from the other side, so that'll give us pi is equal to 2 pi times our path length difference. We can cancel a pi out from both sides. Now what we're interested in finding out here is what the wavelength is. So we'll multiply both sides by the wavelength, and that'll give us the wavelength is equal to twice times the path length difference. Our path length difference was 1 meter, so that means our wavelength will need to be 2 meters in order for our initial conditions to be satisfied. Now, in order to figure out what frequency this is, we have to relate it to the speed. This is radio waves, so that means we're talking about light. So our frequency will be the speed of light divided by the wavelength. So our frequency is going to be the speed of light, 3.0 times 10 to the 8 meters per second, divided by our wavelength of 2 meters. Which will give us 1.5 times 10 to the 8 hertz. Now 10 to the 6 hertz is a megahertz, so that means this is also 150 megahertz. This is close to the FM broadcast of a standard radio.